Okay, it's our pleasure today to have Mateusz Kwaśnicki, who will speak about extension technique for non-symmetric operators or boundary traces of non-symmetric diffusions. This talk is recorded. If you have a question, please raise your electronic hand and I will unmute you, or you can ask your question in the chat. Okay, please, Mateusz.
Thank you very much. It's a great pleasure for me to give this talk, especially at this particular webinar, because it's a probability and analysis webinar. And the talk is precisely on a very wide line that makes a border between probability and analysis. So if you come from the world of probability, then you would probably like the boundary traces of non-symmetric diffusions part of the title. And on the other hand, for people working more in PDEs, the talk will be about the extension technique for non-symmetric, non-local operators. So this is based on two preprints. One of them is probabilistic, another one is analytic. And I will try to briefly describe the main results and perhaps give you some hints about the proofs. But I'll start with something very, very classical to provide motivation for this study. So what I would like to start with is the classical Dirichlet to Neumann operator in the half space. So by H, we will denote the half space. So we multiply the d-dimensional Euclidean space by the half line 0, infinity. We consider some boundary data on that half space. And we solve the Dirichlet problem in the half space. So we find a function u, which is harmonic in the half space, and which satisfies the given boundary condition on the boundary. Okay, and in order to get uniqueness, we need to assume something about the boundary data. For example, that it's continuous and square integrable, and then we assume something about the solution at infinity. For example, bounded is enough. And then the solution is known explicitly in terms of the so-called Poisson integral. So you can integrate your boundary data, or actually convolve it with what is called the Poisson kernel, and that will give you a solution. And that's a very classical result due to Poisson in early 19th century. And there's a probabilistic interpretation of that result due to essentially Kakutani from 1940s that tells you that you can write this integral as expectation with respect to the Brownian motion. So you consider a Brownian motion running in a half space up to its hitting time, and then take the integral of the boundary data according to the distribution of the Brownian motion at the first hitting time. And that's something very, very classical. And now, what is a Dirichlet to Neumann operator? Well, that's an operator that maps the solution U of the Dirichlet problem with given Dirichlet boundary data to the boundary derivative of that solution along the boundary. So somehow the corresponding Neumann boundary data that will give you the same function. Okay, and you can find an explicit expression for the Dirichlet to Neumann operator for that particular case. Of course, the concept is much more general. You can consider any domain in Euclidean space or even more general setting. But in this case, the solution is fairly easy to figure out because we have an explicit expression in terms of the Poisson integral. So the Dirichlet to Neumann operator K applied to the boundary data F is, well, the boundary derivative, which is just the limit of the difference ratio. And if you divide the Poisson kernel by y and pass the limit, what you will arrive at is 1 over z to power d plus 1. So the Dirichlet to Neumann operator is essentially convolution with that singular kernel. And of course, you need to subtract f to get something meaningful. And you need to understand that principal value in an upper bit sense, but that's not now classical. And you can also work in the Fourier transform, which tells you something else, something perhaps more meaningful in some sense. So the Fourier transform with respect to the x variable of the solution is given by the product of the Fourier transform of the boundary data and the Fourier transform of the Poisson kernel, which is known to be of the form exponential to minus y times the mod of argument. So now if you differentiate that with respect to y for y equal to 0, what you get is an operator that multiplies the Fourier transform by essentially mod psi. That tells you, for example, the following. If you take k square, then that will multiply your function by psi square, which is the symbol, the Fourier symbol of the Laplace operator. So k square is minus Laplace operator, which means that k is essentially the square root of the Laplace operator in dimension d. Okay, so that's a Dirichlet to Neumann operator, and there's another way to view the same operator. This operator generates a certain stochastic process, and that process can be viewed as a trace of the Brownian motion on the boundary. So that's the second part of the talk. So now consider the process in the upper half space that is generated by the Laplace operator. So that's, of course, the Brownian motion in the half space, and we consider it reflected at the boundary. Okay, so here's a sample picture of how we imagine Brownian motion looks like. And what we do now is we restrict the Brownian motion to a very thin strip of, say, epsilon width near the boundary, and we erase everything that is away from the boundary. And we still continue to view our processes as a stochastic process with a certain time, but now it has certain jumps. Of course, if we let epsilon goes to 0, then we will arrive at something that blows up immediately. So we slow down the process appropriately so that in the limit we get something non-trivial, which runs in an appropriate clock. Okay, so in order to do that, we need to define what is called the local time. So we look at the y variable only, so the vertical coordinate of our process, and we see how much time it spends up to time t in the interval 0 epsilon. We normalize it appropriately, so that the appropriate scaling is just 1 over epsilon. And it turns out that this process has a non-trivial limit, which is called the local time of yt at 0. It's a continuous process which increases only when yt is equal to 0. So for example, it's almost everywhere constant. It has almost everywhere derivative equal to 0, as it's like a staircase, double staircase function. It only grows at the set of Lebesgue measure 0. And once we have the local time, we can define the clock of our boundary trace as the inverse local time. So in some sense, every time the local time jumps, we just ignore the corresponding path of the Brownian motion. So it's better to think about this, the epsilon case rather than the limiting case. So that corresponds precisely to wiping the everything that exceeds level epsilon away and just leaving what remains with possible jumps. And if we do this according to the local time, what we arrive is a stochastic process whose path is precisely the trace left by the Brownian path on the boundary. So the path of the subordinate process, so we look at the x component of our process at precisely those times at which y is equal to 0. So that will be a non-trivial process that only goes through red points, whose path consists solely of red points visited in the same order as the original Brownian path visited them. So it turns out it's a very nice stochastic process. It's a Levi process. It's a pure jump Levi process. And you can easily figure out what the Levi measure is, the corresponding Levi measure. This is the measure that tells you how many jumps of given size that process makes. And it turns out to be 1 over z to power d plus 1, which means that our process is a stable process with index of stability equal to 1. So it's a one stable process, or in other words, it's a so-called Cauchy process. And this was first observed by Spitta in 1958, and it's by now also standard, and many extensions of that fact are known. So the third part will be about the famous extension due to Molchanov and Ostrovsky on the probability side and due to Caffarelli and Silvestre on the analysis side. So in the probabilistic language, we keep the same horizontal component. It's just the Brownian motion in RD. But the vertical coordinate now is changed to what is called the Bessel process of dimension 2 minus alpha. That's fractional number. Here, alpha is a real number between 0 and 2. And well, the Bessel process is another diffusion. A lot of facts are known about the Bessel process. And the process that you obtain by looking at the trace of the corresponding two-dimensional diffusion, which is no longer Brownian motion, it's some other diffusion, but it's still a fairly simple one. So that boundary trace turns out to be what is called the isotropic alpha stable Levy process, or the stable Levy process with index of stability equal to alpha. So that observation is due to Molchanov and Ostrowski, as I said. And if you put alpha equal to 1, you recover the classical case that I just discussed above. And there are some differences here. For example, the local time requires a different normalization. So the right normalization is 1 over epsilon to the power alpha. In order to get something non-trivial, that's a correct factor, or correct normalization factor here. Of course, the inverse local time will be a different process. Turns out that you can calculate it, and the Levy measure is, again, of power type form, which means that the subordinator is a stable process, a stable Levy process, which only increases, of course, and the index of stability is equal to alpha half. And the corresponding trace is just a subordinate Brownian motion corresponding to that subordinator, if you prefer that language, which is precisely the isotropic alpha stable Levy process. Now, the interesting thing is when you look at that from the analytical perspective, from the analysis perspective. So the generator of the two-dimensional diffusion is an elliptic operator, a singular elliptic operator with a singularity near the boundary of the following form. You just take the Laplace operator in dimension d plus 1, and you add a linear term with a coefficient which depends on the y coordinate, and it actually blows up near the boundary. It's of the form 1 minus alpha over y times the first order derivative with respect to y. And now if you like to define the corresponding Dirichlet to Neumann operator, you run into trouble because you need appropriate normalization. So just as the local time above needed that exponent alpha, the same happens here. So in order to define the Dirichlet to Neumann operator appropriately, you need a normalization factor. So you no longer take just the boundary derivative of the solution, of the corresponding, well, so-called L harmonic function, harmonic with respect to the operator L, but you need an extra factor here. So you multiply the derivative by y to power 1 minus alpha and get a limit, take a limit as y goes to 0. So if you put an appropriate normalization constant C alpha, then you will get the generator of the isotropic alpha stable Levy process, which is just a fractional Laplace operator. There's another way to view it. Instead of taking the derivative and multiplying it by the normalization constant, you can take a so-called weighted derivative. So you take a difference quotient again, but you put an extra exponent alpha in the denominator. And that's the same thing, of course, for example, by L'Hopital's rule. And the way to figure this out, so I didn't give any details about how Molchanov and Ostrowski identified the boundary trace. But here I will give you a few details. So the crucial observation by Caffarelli and Silvestre from the 2007 paper, the famous one, is that you can express U in some sense in a similar way as you did in the classical case, namely as the convolution of U of the boundary data F with an explicit kernel, which is of the form y to power alpha divided by y squared plus z squared, just as in the Poisson kernel, expression for the Poisson kernel, to the power d plus alpha over 2 rather than d plus 1 over 2. Okay, so now if you divide it by by y to power alpha, then the factor y to power alpha cancels out. And what you arrive at is that limit. And of course, if you pass to the limit, then ignoring all possible singularities, what you get is a well-known expression for the fractional Laplace operator, because that kernel, if as y goes to 0, converges to 1 over z to the power d plus alpha. Okay, and that operator is just a fractional Laplace operator. And you can actually follow the same calculation in the Fourier transformed setting. And the calculations in the Fourier transform world are a little bit more complicated because you get a second order ODE, which is solved by the Bessel function. It's sort of a modified Bessel differential equation. So the solution involves some Bessel functions and is no longer that elementary. And you can calculate the Fourier symbol to find out that this is just the mod of x raised to power alpha. So that somehow confirms that the Dirichlet to Neumann operator in that case is the fractional power of the Laplace operator. Now, as I said, this calculation is due to Caffarelli and Sylvester, but on the other hand, the calculation in terms of the Fourier transform in some sense goes back to the work of Mackenhoff and Stein from 1965, and very similar results have been around, at least in 3 different places from different perspectives. But the explicit calculations I show you here is certainly due to Caffarelli and Sylvester. And that paper somehow made everything so explicit that people started understanding that well and using this in many different problems. So this is what is now called the Caffarelli-Sylvester extension technique. And it turned out to be a very fruitful method to tackle very different problems in different worlds, and became quite popular in the PDE world, as far as I can tell. And various extensions of that are now known. So let me mention a few of them. This list is not meant to be complete. So I'm very sorry if I forgot your name here. These are just a few works that I know and that are related to what I'm going to discuss in the later part of the talk. So in this very similar way, one can define fractional powers of more general operators. So if say L0 is an elliptic operator, then one can define a very similar extension problem with the Laplace operator acting in the x variable replaced by L0, and hope to obtain an expression for the fractional power of minus L0. And that actually works very well, especially when you look at the Fourier transform proof, that you clearly see that there should be no problems in doing that, at least in the L2 setting. And that has been done by many authors. So here are some works mentioned. There are some works mentioned here, but the list again is not complete. You can try to extend everything in a slightly different direction. So instead of replacing the operator, the Laplace operator by a more general elliptic operator, you can try to construct a similar problem for more general functions rather than just a power function. And that's what I studied with my PhD student Jacek Mucha in our paper from 2018. We construct the extension technique for complete Bernstein functions of the Laplace operator. And the extension will be, in fact, discussed a little bit later in a slightly more general setting. It turns out that the extension problem exists for a function of the Laplace operator if and only if the function is so-called complete Bernstein function. And actually, after we worked out all the details here, we learned that in the paper by Caffarelli and Sylvester, at the very end, there's a question about what operators can be obtained in that way. And it turned out that we answered that question, but actually we haven't been aware of that. There's such a question in that paper. And then this was even further generalized, at least in 2 works, by combining the 2 approaches. So the first one is the work by Assing and Hermann. Preprint appeared in 2019. And another one, very recent, which is very, very general and allows for a similar construction for very wide class of elliptic operators, L0. and general complete Bernstein functions psi. In the remaining part of the talk, I will discuss an extension which is a little bit different and tries to answers the following questions. So what happens for derivatives of fractional order which are no longer symmetric? So this has been known, as far as I know, only in a one-sided case and derivatives of order less than 1, in which case you can think that the original operator L0 is no longer symmetric, but it's still a nice elliptic operator. It's just the usual derivative, which generates the uniform motion. So you can actually apply the same technique with L0 replaced by, with a Laplace operator replaced by one-sided first-order derivative. But other than that, if you consider non-trivial, not one-sided, two-sided fractional derivatives, or even one-sided fractional derivatives of order greater than 1, then as far as I know, there have been no method to construct an extension technique for these operators. In the probabilistic language, the question is, can one represent non-symmetric stable Levy processes as boundary traces of certain diffusions in dimensions, in higher dimensions? This question makes sense in essentially arbitrary dimension, but it's most meaningful in some sense in dimension 1. And that's the only case that we'll consider. So from now on, everything that happens in dimension 1, if you think about the boundary, and in dimension 2, if you think about the extension problem. Okay, so from now on, D is equal to 1, and we work in dimension D plus 1, which is just the usual plane. So that makes me very happy because I can show you some pictures. Okay, so we move to part number 5, which is about the main result in the probabilistic language. So part number 6 will be about examples, and part number 7 will be about PDE formulation of the results. So if you don't care about probability at all, then just ignore part number 5, have a look at the pictures in part number 6, and then wait for part number 7. So we need a few definitions. So here is what we'll consider. This is something that I call a shift invariant diffusion. So a shift invariant diffusion is a diffusion process, meaning it's a continuous strong Markov process that takes values in the upper half plane. So the product of the real line and the half line 0 infinity. In some cases, we want to restrict to a strip rather than a half line. So in this case, we multiply by interval 0r. What is shift invariance? That means that the diffusion is in some sense invariant under horizontal shifts. So vertical shifts can well change our diffusion, but horizontal shifts should not. Okay, so formally speaking, the law of the diffusion shifted by p to the right is the same as the law of the original diffusion, but started at a different point. So in the subscript, I will always give the starting point. So we change starting point x, y to p plus x, comma y. Okay, that's what I call shift invariance. So it's not really translation invariance. It's only invariance under translations in horizontal directions. Not sure if the name is very good, but I couldn't figure out a better name. And the other condition is that if the lifetime of the diffusion is finite, so we allow for killing in some sense, then at that lifetime, the process either goes to infinity or approaches the level capital R, and the capital R is precisely the upper limit of our strip. So that tells us that the process is never killed inside the domain. It is reflected at the lower boundary at y equal to 0 and killed at the upper part of the boundary if it's finite, or also killed at infinity if it can reach infinity at finite time.
What is lifetime?
What is its lifetime? Well, okay, so processes, Markov process can be killed. Formally, it's defined by moving it to a special auxiliary point, which is often called the symmetry point. You can just think that it's only defined up to certain lifetime, which is typically called zeta in that theory. and afterwards it's no longer defined, and any function that depends on the process from that point on is defined to be zero. So in some sense, that allows you to handle sub-probability measures rather than only probability measures in the analytical language. Okay. And in fact, what we'll be interested most is a regular case in which actually we impose much more stringent restrictions on our diffusion. We say that a shift invariant diffusion is regular if additionally the vertical coordinate is just a Brownian motion and the horizontal coordinate is a local martingale. So in some sense, the drift is no longer present. Okay, and especially if you don't speak probability language and you prefer analysis, it's probably better to look at the pictures. So here's what is meant by these definitions. So we have a diffusion in upper half plane or sometimes in the finite strip. I mean, it's infinite in the horizontal direction, but it's finite in the vertical direction, which depends in a way that is invariant under horizontal translations, but it can depend on the vertical position, so distance from the boundary. So here is a picture that kind of should show a process that evolves more in the, or has more activity in the vertical direction rather than the horizontal one when it's close to the boundary. Then it moves more or less like the Brownian motion, but it has a lot of drift to the right. So if it moves from here to there, it gets a lot of shift to the right. And then from some level up, it behaves just like the Brownian motion. Okay, so the path of this diffusion can look a little bit weird, but that's something that is a sort of typical shift invariant diffusion. And you can add absorption at a certain level. So if R is finite, in the other case considered here, you just do the same. But if your process reaches a certain level, we say we kill it, but it's probably better to think that we absorb it, and everything here, every function here, it must be necessarily zero. All right. So if you like Ito calculus, then you can think that essentially shift invariant diffusions are Ito diffusions with coefficients that only depend on the vertical coordinate, but not on the horizontal coordinate. Okay, so the Ito differential of our process is some matrix that may depend on yt times the two-dimensional Brownian motion, plus some vector that again may depend on yt times dt. Okay, so that's the diffusion coefficient, the local martingale part, and that corresponds to the drift. Okay, that's a general case. And in the regular case, we actually assume that y is a Brownian motion itself. And there's no drift because our process is a local martingale. So things simplify a little bit. And in the regular case, dyt is just Brownian motion. So let's call it dbt2, the second coordinate of our two-dimensional Brownian motion that's somehow in the background of the process. And dxt has a certain factor times an independent Brownian motion plus a certain factor times the vertical coordinate. And that's it. That's not strictly true for at least two reasons. One of them, the simple one, is that you need to add a reflection, and that we know well how to do it using local times. And the other reason is that, in fact, our setting is a little bit more general. So we allow sigma to be somehow singular. So it can be measure valued, it can be zero at some certain parts of our space, and so on. So Ito calculus is not enough to handle all possible cases, but it's a good way to think about what shift invariant diffusions are. And if you prefer PDEs, then here is what you should think about rather than stochastic processes. So these stochastic processes are generated by certain differential operators. And these operators are, well, essentially general second order operators with coefficients that only depend on y, but not on x. Okay, so the general shift invariant diffusion has a general second order elliptic operator as its infinitesimal generator. And in the regular case, actually, we have some simplification. So the coefficient at second order derivative with respect to y is equal to 1, and there's no first order term. So things simplify a little bit. Okay. Now, so that's about the diffusion. Now, what happens with the boundary trace? So we need another definition. So the boundary trace will be a Levy process. That's a general fact. If we start with anything that's translation invariant in the Hall space, then the boundary trace will also be translation invariant and Markovian, which means it will be a Levy process. And we say that a Levy process, a one-dimensional Levy process, has completely monotone jumps if the Levy measure, which describes the jumps of our process, has a density function, which we call nu of z, such that the nu of z and the nu of minus z are completely monotone on 0 infinity. Completely monotone means that the derivatives have alternating signs, but it's probably better to think that they are Laplace transforms of non-negative measures.
Mateusz, there is a question from Alexander.
Okay, hi. I have a question. If we return to the original problem to fractional Laplacian, does it mean that it is not regular case in your sense?
Yeah, so the formulation used by Caffarelli and Silvestre and used by Molchanov and Ostrowski is not regular in that sense, but it can be easily transformed to a regular case by a simple change of variables. I will discuss that for the general case in
I get
the last part.
I get.
So essentially what one should think about is that every shift invariant diffusion can be made regular by appropriate modifications. Okay, so once again, a Levy process has completely monotone jumps if the Levy measure has a density, which is the Laplace transform of the non-negative measure on the positive half line and a mirror image of such a Laplace transform on the negative half line, which tells you in some sense that the structure of jumps is very, very regular. It cannot have arbitrary jumps. So for example, if it has a certain amount of jumps of size 1, that it, say, greater than 1, that it will have a certain amount of jump size, say, between 1/2 and 1. That's a pretty restrictive condition, but turns out to be optimal for that particular case. And I become interested in processes with completely monotone jumps for completely different reasons. I studied Wiener-Hopf factorizations of these processes and was surprised to figure out that in the symmetric case, these are precisely the processes that can be obtained as boundary traces of two-dimensional diffusions in a half plane. And the reason I started studying this subject is that I asked myself a question: what happens in the non-symmetric case? And that seemed to be very difficult until we found a key that unlocked the door, and I will mention the key in a minute. But first, let me state the theorem. So the theorem tells you that the boundary trace of any shift invariant diffusion is a Levy process with completely monotone jumps, and vice versa. For any Levy process with completely monotone jumps, you can construct, or actually you can prove that there exists. It's not a constructive proof. You can prove that there exists a two-dimensional diffusion, shift invariant diffusion, that leaves precisely your favorite Levy process as a boundary trace. In fact, we prove even more that for regular diffusions, this is a one-to-one correspondence. So that gives you a bijection between regular shift invariant diffusions and Levy processes with completely monotone jumps. Okay. So as I said, this was only possible thanks to a key we got from the paper by Eckhart and Kostenko from 2016, a paper published in Invenciones that extended well-known in some group of people studying these kind of things, so-called Krein's spectral theory of strings. I very much like this name because it has nothing to do with string theory in quantum physics, and it can be very misleading. It's also little to do with strings in music, so to say.
Mateusz, may I ask one question?
Sure.
When you say boundary trace, you don't multiply by y to the alpha, it's just actual trace, right? Derivative, boundary derivative, right?
Well, okay, so boundary trace is always measured in the local time of the diffusion, right? If you want the PDE formulation, just give me another 10 minutes and you will see that.
Okay.
So in the regular case, indeed, you don't multiply by anything. In the general case, you need to multiply and you need to do some other stuff in order to get the proper definition of the Dirichlet lemma.
Okay, so you suggest to think in a probabilistic way at this moment, right?
Yes. So in the probabilistic language, you can just think that if you just connect the dots, I mean, not connect, but consider the red dots on the boundary, then there's a stochastic process that has precisely this range in a certain clock, and that's a nice Levy process. All right. So there are other tools used here, and I would really love to tell you a few words about the proof, but I'm afraid I will not have time to do that. So the main ones are additive functionals or Brownian motions. That's something that is used a lot. And in fact, I was very surprised that some results from Markov additive theory of Markov additive processes was needed. In fact, what is a Markov additive process? It's sort of a generalized Levy process that has two components. One of them is just a Markov process, and the other one is a Levy processes with a Levy behavior dependent on the first one, on the first process. So here, the regulator part, the first process, is just the vertical component, and the horizontal component is essentially a continuous Levy process with characteristics that depend on the y component. So our process is an example of Markov additive process, and some results from that theory, which is much more general, in fact, were really essential for the development of that one. There's a lot of technicalities related to local times, inverse local times, and time changes. And in some sense, the ethos lemma is also used in order to handle a certain sort of characteristic function. So the Fourier transform of the x component given the y component. So the proof is sort of follows a well-known path in some sense, but you need to really be very careful because the setting is very general. And for example, you can't just use ethos lemma right away because your process is not regular enough. It's not an ethos diffusion, for example. So you need to do a lot of work first in order then to apply ethos lemma more for something more regular than your original process. Let me just mention that there are two reformulations of that result available. One of them is in terms of functional of Brownian motions. So the easiest way to state it is that if you just take the integral of the vertical component, ethos integral with respect to the vertical component, the dot here means that we only integrate with respect to the martingale part, so ignore the local, the local part in the Ito Tanaka expression for yt. So such integrals evaluated at the inverse local time are, of course, Levy processes. The interesting part is that they can approximate any Levy process with completely monotone jumps in an essentially unique way. There is also a reformulation in terms of excursions of shift invariant diffusions. So instead of looking at the entire diffusion, you can start it at the boundary, it gets killed immediately, we can somehow compensate for that. And what you get is so-called excursion. And you can also describe the result in terms of these excursions, namely the distribution of the excursion at its lifetime is distributed along, distributed just as the Levy measure, the distribution is given by the Levy measure nu of the corresponding Levy process with completely monotone jumps. Okay, let me move to examples. This is the part that I like the most because I can show you a lot of pictures. So in these pictures, I will show you a few regular shift invariant diffusions. So the y component will always be the Brownian motion. And the way these are constructed is using two independent Brownian motions. which I call BT1 and BT2. So BT1 corresponds to only horizontal activity of our shift invariant diffusion, and BT2 corresponds to the vertical one, but the vertical one can be tangled with the horizontal one. So actually the vertical component need not be purely vertical. It can have also some horizontal component. So that horizontal component is given by B of YT, where B is the coefficient in the generator, in the expression for the generator. Okay, and the horizontal part also has a certain coefficient sigma. Sigma is related to coefficients A and B in the expression for the generator. Using that formula, A is equal to sigma squared plus B squared. Okay, so these two lines, the blue arrow and the green arrow, will be called diffusion directions. And if you draw lines that are tangent to either blue arrows or green arrows, you will get something like the profile lines of your diffusion. Okay, so the picture looks, the typical picture will look like that. So you will have activity, some activity along blue lines, some activity along green lines, and the longer the lines are, the larger the activity is. And the process, if there are no green lines, the process will align to blue curves, which I call profile lines. And essentially it will move along these lines, but since we have a local martingale and these lines can be curved, there's something that I call apparent drift. So it will move from one profile line to another according to red arrows. This is not a true drift, that's why I call it apparent drift, but it kind of shows what would be the drift if you made the blue lines straight by what I call shearing. Okay, so here are the pictures. So this is the first one with no green lines, so no horizontal motion. That's a very artificial example. So the drift coefficient, the coefficient that tells you what is the correlation of the vertical and horizontal activity is given by just the sign of y. So the profile lines look like cosines. These are integrals of b. And the process essentially moves up and down along these shifted graphs of the cosine function. But due to apparent drift, it moves from one profile line to another so that it stays a local martingale. Okay, so here's a typical trajectory. The process starts here, and if it moves up, then it also gets a sort of apparent drift to the right until it moves up above pi over 2, in which case the apparent drift changes its direction. So it moves from one profile line to another, one to the left, and so on. And at some point, it goes back to the horizontal axis and leaves a dot that used to be red, but now is blue for reasons that I don't really understand. I made these pictures for the article rather than for the talk, and then I decided to change the colors. But I didn't have the original source files to change the colors also in these pictures. So sorry for that. Okay, so that's just one example. Another example without green lines, without horizontal motion, is given here. So here, this is a less artificial example. So we consider b equal to y to power 1 over alpha minus 1 with alpha equal to 0.4. So here the apparent drift is always directed to the right. And it turns out that the process will only have positive jumps. And due to scaling, it is easy to see that it will be an alpha stable subordinator. So that's a way to interpret alpha stable subordinators. If you increase alpha, then you get still the same picture, but with a little bit more activity, with less drift, until you reach alpha equal to 1, in which case you get a different picture. Now the apparent drift moves our process to the left, so the boundary trace will have only negative jumps. Maybe I'll move to another one where it is more clearly visible, corresponding to alpha equal to 1.6. So the process will essentially, the diffusion will essentially move to the left, but then when it hits the boundary, because the profile lines are tangent to the boundary, it will get a kick to the right. So it will get some kind of continuous drift to the right, and that will lead to an alpha stable process with no positive jumps. Okay, let me show two more examples. One with where there is horizontal activity 2. So that again corresponds to alpha less than 1. In this case, we get an alpha stable Levy process, which is non-symmetric but has both positive and negative jumps. And the same picture for alpha equal to 1.5, in which case we see that there's a lot of more activity of the process. So these are extension problems for non-symmetric stable processes. And finally, one more sort of artificial picture that corresponds to sigma, which is no longer a function. It is a measure, which is a purely atomic measure. And the function b is piecewise constant. So in this case, I don't have time to get into details, but you get a very artificial process that leads to what is called a phase type Levy process. That has been studied a lot also, especially in applications, because it's very easy to simulate and calculate various things. Okay, let me come to the section which is perhaps most interesting to at least some of you, PDE formulation. So the definitions are here somehow simpler. So a shift invariant elliptic operator is just the generator of a shift invariant diffusions that I already discussed before. So it's a general second order elliptic operator. And I don't really want to speak about the regularity of the coefficients because then you immediately fall into trouble. In fact, what we would only consider is the regular case, and in which case the generator of the regular shift invariant diffusion is of that form. So we have a coefficient A at dxx and coefficient 2b at dxy and coefficient y1 at dyyy, and no linear term. And here A is a locally finite measure or a random measure on 0 infinity or 0r, depending on whether we consider finite or infinite case. B is locally square integrable. And we assume ellipticity condition, which tells you that the matrix with coefficients A, B, B1 is non-negative definite. So these are absolutely minimal regularity conditions that allow you to pose the problem formally. And here's a proposition that you asked, Pata, I think, which tells you essentially, it's not really rigorous, but it tells you that essentially every operator L can be regularized by 3 operations. One of them is change of scale. So you just replace y variable by a function of it. That allows you to set the coefficient at the vertical drift, so E of y equal to 0. Then you normalize your operator. You only want to discuss harmonic functions, so constants do not matter. So you can multiply your operator by whatever function you want. So if you multiply by 1 over c, that makes c of y equal to 1. And finally, you can somehow shift parts of the space a little bit to the left or to the right in order to make the coefficient at dx, which was called d of y, equal to 0. And well, that's called shearing according to a profile function tau of y. And using these 3 operations, you can turn any shift invariant operator into a regular one. Okay, so now to answer your question, how is the Dirichlet Neumann operator defined? Well, in the regular case, it's just the usual boundary derivative, plus some extra term if you want to get full generality, but let me ignore that part for the while. And in the general case, you need to regularize your operator, take the usual Dirichlet Neumann operator, and then go back to the original variables, which leads to a very complicated definition involving these 2 functions that appear in the shearing and in change of scale. So the definition is sort of complicated, but it's in fact a natural one, the only one that you can handle, really. Okay, and here U, of course, is a solution of LU equal to 0 with given boundary data, but making this the meaning of the word solution here formal is quite a bit of work. So here is the theorem. So the theorem tells you that for every shift invariant elliptic operator L, the corresponding Dirichlet Neumann operator is essentially a Levy operator with the corresponding kernel nu of z being completely monotone on the positive half-line and the mirror image of something completely monotone on the negative half-line. Plus some
Mateusz, there is a question.
Yes.
There is a question. Okay, David Lee.
Hi, Dave.
Sorry, give me. So, hello, can you hear me?
Yes.
Hi. I'm just a bit curious about your definition of the Dirichlet Neumann operator. So you have this the measure valued at the point 0, and you've got the second derivative. So the stuff in red is that.
Yes, I'm not sure if I understand. Are you asking about that part?
Yeah, this is about this part. So I think this looks like a Wenzel boundary condition, actually.
Yes, you can think about that.
Yeah.
Yeah.
Okay, sure. Okay, it's just a yeah.
You can of course somehow put it into the other side and then say it's a boundary condition for different boundary condition for you. Yeah, of course.
Yeah. Okay. All good. Okay, thank you.
That's only needed, in fact, to get the full generality in the theorem that follows. Okay, so the first part tells you that Dirichlet to Neumann operators have a kernel that is completely monotone on 0 infinity and a mirror image of something completely monotone on -infinity 0. And the second part tells you that this is actually a bijection between regular shift invariant operators and operators, Levy operators of that form. So Levy operators with that kind of kernel. Okay, so that's a one-to-one onto mapping. Unfortunately, it's not explicit. So if you tell me your favorite non-local operator, I probably won't be able to tell you what the corresponding extension problem is. But the good news is that it exists. And at least in some applications, that's enough, because you can apply general results for local operators to get some knowledge about your non-local operator. So let me just mention in the end that the proof of that theorem is in fact essentially different from the proof of the probabilistic counterpart due to technical issues. So in principle, there's a simple way from one theorem to another. But if you like to work in that generality, you fell into trouble. Just as I said, it is, for example, difficult to use the Ito lemma to get the probabilistic result from the analytical one. So the key ingredient is again the result of Eckert and Kostienko, but here we use Fourier transformation in the x variable, and the framework is pretty straightforward here. You just need to define your solutions very carefully. So you need to speak very carefully about weak and distributional derivatives, use certain fancy properties like absolute continuity on lines, and a lot of other technical details. So as I said, the path is clear. You just need to make your way through it. And once you do that, you get the desired result. And my time is up. I think I extended that by 4 minutes, so I'm very sorry for that. And thank you very much for your attention. If you have any questions, I'll be happy to answer.
Thank you, Mateusz. Thank you for the very nice and great talk. Okay, if there are any questions, I will give you permission to unmute yourself, anybody. You can just unmute yourself and ask a question.
Okay, may I have a question. Actually, I have two questions. The first one is when I think it was section 4, when you were talking about your joint result with Muha, and you were talking about which processes you can get on the at the border, on the horizontal line. And you mentioned Bernstein functions, and then you referred to result by Caffarelli. I'm very ignorant with stochastic processes, but I have a vague memory of hearing something in the theory of Feller processes when you look at two notions of subordination. One is taking the generator of your Feller process and stick it inside Bernstein function, and another subordination, just the change of time. And I have a kind of vague memory of someone saying that these two things are kind of equivalent. They produce the same processes. Is it somehow related to what you mentioned in your section 4?
Well, I don't think it really is. So it's pretty clear that the process that you get will be a subordinate Brownian motion in the sense of Bochner, because what you look at is the horizontal coordinate in the symmetric case. What you look at is the horizontal coordinate, which is time change Brownian motion, evaluated at times that are given by the inverse local time of the vertical coordinate. So you precisely take the Brownian motion at the times which are given by some increasing local Levy process. So by definition, this is a subordinate Brownian motion. The true meaning of that part is that what you get is what is called a complete subordinator, or in other words, a subordinator with a Levy density that has a completely monotone density function. This is not really so new because all the pieces were already around at least since 60s. So actually, Molchanov and Ostrowski could have written the paper in greater generality because all the pieces were already there. And this was, so the main contribution of the paper is joining these pieces and filling in the analytical details. So there is actually very little probability there. I don't think we have any section on that. It's just short mention of probabilistic meaning, because the probabilistic meaning is pretty clear there. The devil sits in the details on the PDE side, actually. So formulating the problems carefully, proving everything in the L2 setting and so on was the main contribution of that paper. Here in that part, I think even the probabilistic part was missing. And in the non-symmetric setting, I don't think much was known about.
Okay, thank you. And the second question was, so as far as X is concerned, you have the whole line. Has anyone looked at the problems where, say, in X you have, say, half line? So basically, your Brownian motion is in the, the diffusion process is in the quarter plane, and then when you restrict to the boundary, you get half line, and say, then you get a Levy process on a half line, and you might have, I don't know, kill process, censored process, reflected process, depending on which boundary condition you have for the diffusion process. Has anyone done anything like that?
In the symmetric case, I think something similar has been done. I mean, people did the extension problem for the reflected Brownian motion and other types of Brownian motion with different boundary conditions, even more general ones. But in this non-symmetric setting, that's actually a very interesting question. I don't think even in the simplest setting, in simplest cases, anybody looked at that. So certainly you can construct extension problems for various no longer Levy processes in domains using that, but honestly, I have no idea what would that correspond to in the non-symmetric case. It's actually a very, very interesting question. Probably worth studying.
Thanks. There are 3 other questions. Let's do in this order. Galina, Alexander, then David. Galina, please.
Thanks, Vada. Thanks for the talk. Yes, I just wanted to ask if there is any meaning in considering a kind of dual operator, and if you can construct all the theory, if instead of considering the Dirichlet-Neumann operator, you would fix the Dirichlet data to be 0 and Neumann data to be 0, but you would let your operator to be some mean zero function on the domain, and your space, and then you would have an operator acting on a say so many functions on the domain into itself, rather than functions on the boundary. That would understand what I mean. That would correspond a function which is a solution of that PDE to the corresponding other solution.
So something like a Neumann to Dirichlet operator, is it right?
I don't know. It wouldn't make sense if it's Neumann to Dirichlet, because Neumann to Dirichlet logically would be the just inverse of the operator, but
exactly.
At least logically.
So I've had some troubles hearing you actually. Can you perhaps repeat the question maybe?
You know what, how about, because there's many questions, let me write it in the chat while others are asking.
Okay.
So I'll mute myself and write it instead.
Okay.
Okay. Alexander, please.
Okay. Mateusz, I have a question. What do you think about problems in multidimensional variants of your theory?
Yes, of course, that's a very natural question. What happens in higher dimensions? So if you just look at sort of some kind of dimensional analysis, so how many parameters you have and how many processes you would like to obtain, it's pretty clear that you can't hope for a result as general as that one. And I of course, thought about that a little bit, but honestly, I don't see any clear picture here. So I don't know if there's any nice characterization of the process that can be constructed as boundary traces of non-symmetric higher dimensional diffusions like that. Yeah, that's probably all I can say about that. That's a very interesting problem related to Calderon's problem of characterizing sort of Dirichlet-Neumann maps for general domains. But I don't think.
Okay, and also I have a comment that in a standard case, in classical case of fractional Laplacian, you can consider the Neumann to Dirichlet map, which corresponds to the negative power of operator in the simplest case, in the case of the whole space. In the case of domain, it's not so, but anyway, what can you say about such idea here?
Well, it's a general principle. I think that if you consider the inverse problem, I mean the Neumann to Dirichlet, then if it's well posed, then that will correspond to the inverse operator. So that will be inverse operators of that form, which are essentially what's called potential operators corresponding to these Levy generators.
Yes.
And I think there is a characterization of these. Certainly, in terms of Fourier transform, you can fairly simply write them. I'm not sure if there's a simple characterization in terms of kernels. I would need to think about that. But yes, of course, you can formulate a result like that, but just looking at the class of operators which are inverse to these operators K. And these are fairly well understood from the potential theoretic point of view, at least.
Okay, thanks. And well, I have a question to the organizer. Where will it be, where the record will be placed?
It will be placed on the official webpage of the seminar. I can put it in the chat right now.
Okay, please.
Yes, we have a
by the way,
YouTube channel.
The chat is disabled, so I'm.
It's disabled. Thank you, Gala, for letting me know about this. I will enable it right now. Okay, now it should be enabled, and here is the website of the seminar. It should appear in 1 or 2 days, depending how quickly the video will upload on YouTube and will process.
Great.
Okay, and there is a question from David. David, please.
Hello, can you hear me?
Yes.
Okay, so firstly, thank you very much for this talk. It's very fascinating. There's several questions for myself. Just a sort of a bit of a naive question. So this the shift invariant elliptic operator. So I'm assuming that you define that via form. So I'm assuming that the form is also non-symmetric as well.
I'm not sure if I understand correctly. This was about symmetry. Maybe your mic is too loud because
yes, your microphone is too loud.
Okay, I'm sorry. Let me give me 1 second. How's this now? Can you hear me a bit?
Oh yeah, it's
great. Now it's great.
Oh, okay. Thank you. Okay, sorry about that. So just so in terms of the form, is it the form associated with this operator? I'm assuming it's is it also non-symmetric? The form is a non-symmetric Dirichlet form.
Yeah, I suppose so. I mean, I know next to nothing about those traditional forms, but
Okay.
yes, it's so this the process that's generated by K is certainly non-symmetric in general. So the corresponding bilinear form must be non-symmetric too. And
Right.
the thing about the corresponding diffusion. So it's a second order operator with matrix, which if you take the dual of it, then you will have the derivatives with respect to y acting also on the coefficient. So you'll get something which is no longer even of this form.
I see. Okay. And in terms of your solution to your Dirichlet problem, is it even though that your form is not symmetric, are your solutions variational in some sense?
No, not really. I don't think so. At least that's not the way it is discussed in the paper.
Right.
So in fact, that the solution is understood in a sort of weak sense, and of course you fall into troubles because you need to put derivatives also on the coefficients in that case, and the coefficients are very irregular. So there's a lot of technical issues going there, but it's understood more in some pointwise sense, I would say. Variational methods are not used here. Unlike as in the other paper, the former one with Jacek Mucha, where actually most of time we think about the energy form and solutions as minimizers of that energy form.
Let's see. Okay. Okay. Interesting. Thank you very much.
Thanks for coming.
Thanks for the question. And Gala wrote in the chat, Mateusz.
I'm just reading it. Consider mean 0f on the domain omega, and let uf be the solution of delta uf equal to f. Trace of uf equal to 0, and let vf be the solution of delta uf. Okay, I'm not sure if I understand what nu is. I think it's a normal derivative, right? So it's
normal derivative, yeah.
And TR.
So you take Neumann boundary condition. There's the boundary condition, but for the same right hand side.
Oh, so the right hand side is non-zero, right? That's
yes.
Thing? Oh, I don't know. I would need to.
But it's still a linear operator. Only this time it's not on the boundary; it's on the domain, and it's somewhat dual. So that's why I'm asking. Like it makes sense just exactly in the same way.
Okay. I don't want to say something that's completely wrong, so I would need to think about that. I have this question written down in chat afterwards, so maybe I'll think about that and we can contact via email.
Thank you. Yeah, I will write you. Thank you. Okay, yeah. So I thought you would be like, but of course, 80 years ago somebody did that. But
it might be something completely different. I don't want to say something that's completely wrong. So I think both are possible. So I need to understand, digest that in some sense and understand that well in order to answer. Sorry.
Thanks.
Okay, thank you. We are a little bit over the time, so let's again thanks the speaker again for the great talk. Thanks, Mateusz, and I hope to see everybody again next week on Monday.
Yeah, have a good day.
Have a good day.
Okay, thank you, Mateusz. Thank you, Pata.